Hello, everybody. Hi, everyone. It's so nice to see so many of you guys here already. I hope you've had a nice Saturday. I mean, you probably have tried to do some studying, maybe procrastinated a little bit, or that's at least what I remember when I was doing my GCSEs. Okay, so we're going to be, in this live stream, we're going to be looking at the first half of the Computer Science Paper 1 topics. On this screen, you can see that we'll be going over components of a computer system and data representation. So this live stream will be slightly different from the other live streams. In this one, we'll be going over all of the content. And the way I'll be doing is as if you're a beginner. So you'll be able to understand it, because I often found computer science a bit difficult. So this is teaching everything from the basics, okay? So we're going over the first two topics, and then on the Tuesday, 14th of May, night before live, we'll be going over networks and issues. There might be some exam questions if we have time, and this live stream is going to end at 6:15 in time for the geography live stream if you're going to be there as well. Okay, now before I get started, it's a mini gift for all of you guys here. It's a free GCSE Computer Science resource for you. So we will be doing I've created GCSE Computer Science mind maps, which link together all of the concepts, and these are what I used for my exam. And so there might be some topics that are not on the spec anymore, and I cross them out for you guys, but they're really useful because they link all the topics together. So if you don't understand my live or any way I'm telling you, then perhaps you will find the mind maps much more easier to understand. Okay, so you can access it by the link in the description box, and let's get started now. There will be paper 2 live streams as well. The geography live stream is literally after this. You should find it on the channel, scheduled. Okay, so the first topic is components of a computer system. By the way, all of the papers, all of these PowerPoints I've made myself, so it took me a long time. So I'd appreciate it if you subscribe if you haven't already and like the live. Computer systems. So, what is a general purpose system? A general purpose system is a computer that is designed to carry out many different tasks. For example, smartphones or a PC or anything like that. Now, general purpose systems can be used to do different things. For example, use word processing software to play games, to store data, to retrieve data. Okay, so anything that you think a smartphone can do, because that's an example of a really useful general purpose system that everybody has access to, that is what you want to do. So general purpose systems have multiple applications. The golden resource, if you go into the description box, and you'll find a link to my website where all my resources are, and you can scroll down and you'll find it there. Now, embedded systems are slightly different. So embedded systems are computers that are found in other devices, for example, dishwashers, microwaves, and TVs. Now, there are advantages of embedded systems. Firstly, they have a very limited number of functions. This means that they are cheaper to design and build. On top of this, they tend to require less power. So some devices run from just batteries. And they don't need much processing power, because what happens is with these embedded systems, they often just have a repeatable set of instructions to follow, and they'll just keep doing that over and over. There's nothing that needs to be changed. Now, general purpose systems are made up of both software and hardware. So, software are the programs and applications that a computer system can run. I'm pretty sure you're aware of it. And hardware is the physical stuff that makes up a computer. For example, the motherboard or the keyboard, anything like that. Now, this is the structure of the general purpose system. You've got inputs, CPU and output. Now the inputs and outputs, you can see the inputs are typically hardware and the outputs can be hardware or software. Now you've also got your primary memory or your secondary storage. Now across this live stream, I'll be going through all of them. So don't worry if it's not ringing any bells yet. So we're now looking at the computer, the CPU and the FDE cycle. So in any computer, there are 4 key components, okay, and they are really important. So you've got the CPU, you've got inputs, as we said, outputs, storage, and the things that make up the CPU. So the main memory, the processor, the cache, and forms of storage are either secondary storage or cloud storage. So, the CPU, what is it? The CPU is the central processing unit. It processes all of the data and instructions that make the system work. And it's really important if you're asked to name or to define what the CPU is, that you use the words it processes all of the data and instructions. Now, let's discuss the first 2 subcomponents of the CPU. You've got the processor and the cache. Both of these have even smaller parts. So the processor is made up of the CU, the ALU, and the registers. So CU is the control unit. This coordinates all activities in the CPU. It's involved in the executing, the decoding, which you will know and you'll understand once we go over the FDE cycle. It's also important for regulating processor timings, because if you think of it, with computers, everything happens at the tick of a clock, and it's regulating that processor timing to see if you can make that clock speed up. Now, the ALU is the arithmetic logic unit. This is the one where most people remember because it's got the name arithmetic in it. So in the arithmetic logic unit, arithmetic operations happen: addition, subtraction, division, multiplication. You've also got logical operations as well, like the AND or the OR gates, which we'll talk about in the paper 2 live streams. And it also has binary shifts, which we'll look at later in this stream. And finally, registers. Registers are a very fast memory location. We'll talk about that in a second. Now, here are the key registers that you need to know. You've got the MAR, the MDR, the CIR, the PC, and the accumulator. Now, you'll be able to memorize it and understand it again once we go through the FDE cycle. I've got a really good animation coming up which goes through the FDE cycle to help you, because almost every year they have a question about it. So going through these, we've got the MAR, which is the memory address register. This is where the addresses, i.e. the locations in the memory, are fetched and stored. So if you're going to make a request, there's going to be, you're going to look for a certain memory, you're going to look for a certain data. Now, that data is going to be stored at a certain address. So the MAR is where those addresses are fetched and stored. We'll be going through CIR in a minute, okay? The MDR is the memory data register. This is where data is fetched from the memory. The CIR is the current instruction register, I believe, and it holds the current instruction from the MDR. It's in the specification, as somebody said in the chat, but what's important to remember is that it doesn't do anything beyond holding the current instruction from the MDR. It's just another step between them. Okay, so it is part of the OCR specification, but it's just not as important as a step. So sometimes teachers don't even mention it, and if you don't put it in your answer, then OCR often doesn't mind. But it's another thing that you need to be aware of. Okay, PC. Now, the PC, the program counter, increments to the next instruction, and the accumulator acts as a temporary store of all of the results of the calculations. So, if you didn't get what we just said, we'll be going through that, as I said, in the FDE cycle. It's just about introducing you to those concepts. So, the cache, what does a cache do? Well, the cache stores frequently used data. But it's not just like any sort of memory holder, storage holder. It is faster to access than the RAM, the main memory. So most of the data in a computer is stored in the main memory. But it would take a long time if you had to keep accessing everything from there. So you've got the cache, which is the frequently used data, which is much faster to obtain. Now, it actually increases the CPU performance. Now, we know all of the components, so let's look at the FDE cycle, which stands for the fetch, decode, execute cycle. And when you want your computer to undergo any task, then the FDE cycle is going to happen. Ethics will be done in the second live stream, which will happen on the night before the actual exam. Okay, so stage 1 of the FDE cycle is the fetch stage. Okay, so what that means is if you wanted a piece of data that was stored in memory location A, imagine we have memory location A over there. The PC, the program counter, sends the address of the next instruction, location A, to the MAR. So imagine the next instruction, we're now on to fetching data from location A. So it sends the PC program counter, sends the address of the next instruction to the MAR. Then what happens is the PC increments. It moves on to the next instruction, okay? So because you've got a list of tasks that you want to happen, it'll move on to the next task. The MAR then sends the instruction or data that's held in location A to the MDR. So that's holding the data at the location. So the MAR is about the address and the MDR is about the data of it. And then the MDR, the memory data register, sends the data at location A to the CIR, this is the in-between step that a lot of you aren't familiar with, the current instruction register. And this is found in the control unit. The instruction or data, we've now moved on to the decode part of this. So the instruction or data is then decoded in the control unit. So remember, when we were looking at the control unit, we were looking at all the different things that happens in it. So it's got the decoding and the executing part of this FDE cycle. So a lot of things happen here. So the instruction or data is decoded in the CU. It decides then whether any further operations need to be done. For example, if you need to do a calculation in the arithmetic logic unit. And finally, execute. The instruction is then executed. Again, this often happens in the control unit, but if it's something that involves fetching data, then obviously that's going to have to go outside and fetch that data from the memory. Now, if you understood that all in one go, then that's amazing, because this topic is a bit tricky at first. Hopefully this should be a bit more revision for you rather than learning, but it's okay if it's either. Hopefully that was clear, and if you have any more questions, maybe put them in the comments because they're more easier to respond to. We're now looking at the next part, which is memory. Now, when a program needs to be executed, the program itself needs to be loaded from the storage to some sort of memory. Now, if we're looking at the difference between storage and memory, storage is for the long term, whereas memory is for short term. Okay, short term retrieval is memory, long term is storage. So when a program needs to be executed, you need to move the data or the program from the storage to some sort of memory so that the processor, which is where the FDE cycle happens, can access that program. And this is why we have the main memory. The main memory acts as that storage. So the main memory, also known as the RAM, stands for random access memory. Now, why is it called random? Well, the word random is important because it means that you can access the data at any time and in any order. So it doesn't matter what time you want to access the data, or if you want to access the third instruction of something rather than the first, you can access it randomly. So, the RAM acts as a temporary storage of programs that are being executed. Hence, computer scientists call temporary memory volatile memory. But sometimes the RAM gets fully used. It's got a limit, a capacity which it can't go over. But the user still needs more space. So what is the solution? It's something called virtual memory. So the virtual memory is a piece of storage that disguises as extra RAM, and where the memory that's used less goes into to make more space in the RAM for things that you're accessing right now. Okay, now, what is the issue with this? Virtual memory is really slow, and you need to know the disadvantages of it. It has slower access speeds, and you may have experienced this yourself when you have loads of different tabs open on a window, and then the computer starts to buffer and take longer. Hence, virtual memory is not the best solution for this sort of thing. So it might be better for a longer term solution, which involves increasing your RAM space by buying a better computer. Now, the final type of memory which you haven't spoken about is read-only memory, ROM. This is a non-volatile memory source, which means that when you turn the power off, the memory is still retained. It still remains on the computer. Now, this is unlike the RAM, which loses all of the data as soon as the power goes. Networks will be in the next live stream. Okay, now the ROM, the read-only memory, holds information such as the BIOS, basic input-output system, and this is needed every time you open up your computer, and it doesn't need to be edited, which is why it is non-volatile. It stays exactly the same. Exactly, the ROM is needed to activate all life in the PC. Now moving on to the next topic, which is factors affecting the CPU performance. Now, the CPU's performance is based on four main things, which is cache, clock speed, RAM amount, and number of cores. For those asking when is the next live stream, please just look at the live stream timetable that I've released, which is also on my website, or if you find it somewhere on the community tab. Okay, so these are the four things that impact the CPU's performance. So let's start with looking at the cache. Now, as we said, the cache is data storage inside the CPU that has much faster access speeds than the RAM. So a larger CPU cache gives the CPU faster access to more data. Now, clock speed is another factor that impacts the CPU performance. So, everything in the processor, as we said, runs at the tick of a clock. The number of instructions a single processor can carry out per second is measured in hertz, and this is known as the clock speed. Hence, the faster the clock speed, the greater the number of instructions that can be carried out per second. But sometimes, if it is too high, it can cause the CPU to be overclocked and result in crashes, and even it could have permanent damages. Now, RAM amount. The more RAM, the more random access memory you have, the less the reliance you have on virtual memory, which has much slower access speeds because the less likely it will be full. So that's another impact. And finally, the number of cores. Each processor core can process data one at a time. So the more processor cores you have, the more data the CPU can process simultaneously. However, it is limited to how many cores the computer is originally built to facilitate. For example, if you have a 4-core computer, a quad-core computer, and you want to install software which uses 6 cores, it's only going to use a maximum 4 that your computer is built for. So it's limited by that. Okay, so we're now looking at secondary storage. So far we've spoken about RAM, random access memory, virtual memory, and ROM. But these are only temporary or do not let you edit the contents. So we need a form of storage that lets you both store and edit data. And this is what we call secondary storage. So there are different types of secondary storage. You've got magnetic devices, solid state, i.e., flash memory, depending on what you call it, and also optical memory. So let's now look at the different types in more detail. Magnetic devices. So magnetic devices, such as hard disk drives, use magnetic fields to magnetize tiny individual sections of a metal spinning disk. You don't need to know this in detail, you just need to be aware of it. Each tiny section is supposed to represent one bit. So a magnetized section represents a binary 1, and a demagnetized section represents a binary 0. These sections are so tiny that disks can contain terabytes of data. Now, it has advantages and disadvantages that you do need to be aware of. So, advantages. It has a very high memory capacity, but disadvantages are that the moving head is vulnerable to magnetic fields, i.e., it can easily get damaged, and on top of that, it's easily susceptible to any physical damage as well, apart from magnetic fields. Solid state, aka flash memory. Now, this uses non-volatile random access memory to store data indefinitely. They tend to have much faster access times than other devices or other types of devices because they have no moving parts. So solid state tends to be the most chosen one. Now, advantages: it requires very little power, it's portable and is quite durable. Disadvantages is that it's expensive and tends to have a smaller capacity. Finally, optical memory. Now, optical devices use a laser to scan the surface of a spinning disk made from metal and plastic. So the disk surface is divided into different tracks, and each track contains flat areas and also hollow areas, so pits and lands, and they are read as either ones or zeros in binary. Now, advantages of this is that it's lightweight and portable. But disadvantages is that it can lose data when the surface is scratched and it doesn't hold much data. If you've ever used a DVD and noticed that it doesn't work because maybe there was a scratch on it, that's quite annoying and it means it's not really a reliable source of data. Okay, we're now moving on to the next part, which is looking at system software, the operating system. Now, an operating system is a very complex piece of software which is found on most computers. It's the bigger program that controls a computer. Now, functions of an operating system. Firstly, it manages user accounts for security, communicates with internal and external hardware via drivers. Now, you also need to be aware of all of these as well. It provides a user interface. It enables multitasking via monitoring the memory and CPU. It coordinates file management and disk management, and it provides a platform for different applications to run. So let's now go individually at all of these. So device drivers, what are these? Well, device drivers are basically software that communicates between the internal hardware of peripherals. For example, here, you can see that the operating system will detect any new hardware signals and then install the matching driver. For example, if you're trying to match your if you're trying to find a printer, a local printer, what you're going to do is do the same method, and then it'll come up as one of your different options, and that's the device driver. So you have to then install the driver to be able to access and send things to that printer. Now, every piece of hardware connected to a computer system requires a device driver. Okay, let's now look at the next function of an operating system, which is looking at user interface. This allows the user to interact with a computer system. So you've got the graphical user interface or the command line interface. Now, for a long time, computers used to just be command line interfaces, which is where you effectively had text, which was simply a text-based interface. So you simply entered commands, and it was often in quite difficult and they had very strict regulations of what things you could enter. They were very specific, and these are less resource heavy. For example, they're less energy intensive when you're using them, but it requires the user to have a certain level of experience with it. However, you could possibly have greater user control than a graphical user interface. So a graphical user interface, for example, WIMP, windows, icons, menus, and pointers. So those are the different things that are part of a graphical user interface. But now we also have iOS and Android, which have different swiping gestures or pinching gestures on top of using a mouse. Now, this is an example of what a command line interface looks like. You may have accidentally pressed a key on your keyboard and seen this before. Okay, now this is what a graphical user interface looks like. So which one would you say is much more user-friendly? And which one would you say also has more user control? So here is a reminder of what we've done so far. So we've spoken about drivers and we've spoken about user interface. We're now going to speak about multitasking. So multitasking is when an operating system can run multiple applications at the same time. So you need to know how the operating system helps the CPU carry out multitasking efficiently. So when an app is opened, the operating system moves only the necessary parts to the memory. It may also remove any unused apps. It then divides the CPU time to ensure that only one app is being processed at a time, and it's also responsible for organizing the flow of data into virtual memory. Now, disk management. This is another responsibility of the operating system. So the operating system manages the hard disk by splitting the physical disk into storage sectors. The operating system may also include utility software to help it manage files and disks, for example, disk defragmentation, which is a topic you look at later on. User accounts is another function of the operating system. So you can have a single user or a multi-user account. Now, single user accounts are when the operating system only allows one user to use a computer at once, whereas multi-user is several users to use a computer at the same time. So an example of a multi-user is looking at an ATM. This allows thousands of people to access their bank accounts all at the same time, versus a single user, which might be something like a home computer, which only has one login for one specific user. We're now going to look at system software utilities. So, what is utility software? This is software designed to help maintain and optimize a computer system. For example, things that happen on this are disk defragmentation. This is an example of system software. So files are stored on a hard disk in available spaces, and ideally, files can be accessed much more efficiently if they're stored together. But because files are moved, deleted, and changing size, you just have a lot of small gaps left together. So over time, the disk becomes fragmented, and defragmentation software reorganizes the data and puts the fragmented files all back together. Now, another example of a system software is compression. So you're reducing the file size by either permanently removing data or temporarily removing data. Now we're going to look specifically at compression at the end of this live. But why does this happen? Well, compressed files take up much less disk space, they're quicker to download and also send across. So, lossy compression versus lossless compression. Hopefully, with images, there's not too much differences between them, but with documents, they can actually get rid of words, and that's not very useful. Encryption. So encryption is another example of system software. So it scrambles the data up to stop third parties from accessing it, so that if the data is intercepted or stolen, the data is still secure. Now, as only the intended readers can unscramble the data with an encryption key. Now, you need to be careful with your wording because they often ask about encryption. So you need to mention how if the data is intercepted or stolen, the data is secure because you need an encryption key. Data representation. So we're now on to the second subtopic. We're first going to look at units. Now, a lot of this is just based on maths, so it's not too difficult to go through. So computers use ones and zeros to represent the flow of electricity. 1 is on, 0 is off. So each 1 or 0 in binary code is called a bit. In the binary code 101, you can see that there are 3 bits present. Now, the normal number system we use is called denary, and the ones and zeros are called binary. So binary is base 2 because the values are doubling each time. They're going up by powers of 2. Denary is base 10 because we're going up in powers of 10. Now, these are all of the units of data conversions that you need to learn. So a bit, nibble, a byte, kilobyte, megabyte, gigabyte, terabyte, petabyte. You need to be aware of them because they can definitely ask them. Okay. We're going to just skip these next exam questions because we'll be going through that later. We're now on to binary numbers. So that's what we already learnt. Counting in binary is very similar to counting in denary, but the place values from right to left increase by powers of 2 instead of powers of 10 like denary. So let's look at how the system works. When computer scientists write like that is what each value truly stands for. Now the ones represent the actual respective value and the zeros represent the absence of that value. Okay, there's an exam question if you want. Now, adding binary numbers is a key skill. So adding binary numbers you can do with column addition. So hopefully you know the 5 different rules of binary addition. 0 plus 0 is 0, as you said. As you probably know, 0 plus 1 is 0. Is 1, carry over 0, sorry. 1 plus 0 is the same thing. 1 plus 1 is 0, carry the 1. And 1 plus 1 plus 1 is 1, carry the 1. That's really important to be aware of. So just going through an example here, you can see that the 1 plus 0 at the end is just 1. Then the 0 plus 0 is 0. The 1 plus 1 is 0, carry the 1. And then you've got 1 plus 1 effectively, which is the same thing, 0, carry the 1. And then you've got a triple 1 at the end. So you end up with 1, 1. And then what does that mean? Well, that can mean you can often get the overflow error. Well done for people saying that. So overflow errors, when you get a binary value that requires more bits than the CPU is expecting, they often ask about overflow errors, so make sure you go through that. Computers usually deal with these extra bits by storing them elsewhere. Now on to hexadecimal. So I've already spoken about denary and binary. Hexadecimal is base 16. Okay, so it uses 16 different digits, so 1 to 9, and also A, B, C, D, so letters, 4 values over that, all the way up till 16. Now, here's how hexadecimals work. So you have a single hex character, which can represent any number from 0 to 15, and each hex character requires 4 bits, a nibble in binary. So there you go, you can see the conversions there. You can pause it if you are unsure about hexadecimal. Now notice that from 10 to 15, the hex values are actually alphabetical letters because we're representing them with single values rather than saying 10, 11. Now, convert the hex value 72 into denary. So firstly, understand what base 16 means, which means that there's a table for you. And that's converting base 2, so to the powers of 2. So going through base 16, you've got 16 to the 0, which is 1, 16 to the 1, which is 16, and 16 squared, which is 256. So if you wanted to convert 72 into, I think it means hexadecimal there. Oh, no, sorry. Convert the hex value 72 into denary. So 7. So you've got 7 16s and 2 1s. So if you add them up together, you get 114. Okay, now to convert between hexadecimal and binary, remember that each hex value stands for 4 bits, and so each single hex digit is into a nibble. So you split it up. So if it's an 8-digit one, then you split it up into 4s and 4s. And then if it's an odd number where they don't have 8, for example, if it has 9, then you want to add 3 zeros to the left-hand side. Finally, why is hexadecimal used? So, it's simpler to remember larger numbers in hexadecimal because they're shorter than binary. Also, it's easier to convert between binary and hex values, and due to hex numbers being shorter, there's less chance of input errors. Sometimes they ask about this in the exam, so make sure you're aware of it. We're now moving on to characters. Now, keyboards have roughly 98 unique characters, okay? But computers are unable to process all of these characters directly because computers only process binary code. So computers need to convert the characters into binary code, and they do this via character sets. Now, a common exam question which is asked every year, which is what is meant by a character set. So you want to say character set is a collection of characters that a computer recognizes from their equivalent binary value. Now, there are two types of character sets that you need to know for your exam. You've got ASCII and you've got Unicode. Now, ASCII is the most commonly used character set in the English-speaking world. Each character is given a 7-bit binary code. Extended ASCII is 8-bit, remember that difference, and it can represent 128 different characters. With Unicode, Unicode tries to cover every possible character or symbol. Each character is given a 16-bit binary code, and this means that there's 1,112,064 different combinations. Okay, moving on. You can also work out the size of a text file by this formula. So the file size is the number of bits per character times by the number of characters. This is quite intuitive. We're now looking at the next part, which is storing images. There are two types of images. You've got vector and bitmap. So vector images are made using a mathematical formula, whereas bitmap images are made just using loads of tiny squares, which are all colored in different colors. Now, the color of each pixel for bitmap is represented by a binary code. The number of colors available in an image is related to the number of bits that the code has. Now, black and white images only are using 2 colors. I know the picture here has gray as well, but strictly black and white ones use 2 colors, so therefore they only need 1 bit per pixel because it can either be turned on, which is black, or turned off, which is white. Hence, a 2-bit image has 4 different ways, so it can represent 4 different colors. Now, there are a couple of key terms you need to be aware of. So you've got color depth and resolution. So color depth is the number of bits you're using per pixel. So if you have a higher color depth, then obviously your image is going to be, your bitmap image is going to be much more accurate. And resolution is the number of pixels in an image. So you're doing your length times your width. Now, the color depth can be used to work out how many colors are in an image. So you've got the total number of colors is equal to 2 to the power of n, where n is the number of bits per pixel. And you can also find out the color depth and I went too fast. The color depth and resolution to work out the file size of an image. Now, the final definition is metadata. So metadata is the information stored in an image file. The purpose of metadata is helping the computer recreate the image on screen from the binary data, and you can definitely go into your files and find out the metadata. We're now on to storing sound. So, sound is captured by a microphone as an analog sound. So, analog signals are continually changing data. However, this analog signal needs to be converted into a digital signal. Why is this? This is to allow the computer to understand and store this information. So, this is done by an analog to digital converter. And this whole process is called sampling. So, as samples are taken every few milliseconds, it will store the amplitude, which is the height of the wave, as a binary value. So, if you're taking more samples, then that means that the recording is going to be more accurate. But the larger a file size would be, and this is called the sample rate. Now, if you ever want to calculate the file size, then you just do of a sound file, then you do the sound rate in hertz times by the bit depth times by the duration. Now, bit depth, as we said before, is the number of bits used to store each sample. And we are now on to compression. So, compression is making the file size smaller whilst trying to make the compressed file as true to the original as possible. So, why is data compressed? Well, smaller files take up less storage. Streaming and downloading files from the internet is quicker as they take up less bandwidth. It allows web pages to download much more quickly in web browsers. And email services normally have restrictions on the size of the attachment that you can send. Now, there are two types of compression, as we spoke about earlier, lossy and lossless. So lossy works by permanently removing data from a file, whereas lossless is about making the file smaller by temporarily removing data to store the file and then restores it to its original state when reopened. Okay, and that is the first half of the computer science content. Depending on time, I can practice some exam questions. I think actually instead I will end the live stream here. We're now going to be moving on. We'll be doing the second half of computer science the night before the exam, but that's the first half of the first paper. So thank you for watching this. And I guess I'll see you in the geography one if you're going to be there, or the English literature ones tomorrow. Okay? Bye for now.